Welcome to Chapter 5. In this chapter, we're going to do some heavy lifting here. It's going to be a culmination of a lot of things we've done and almost utilizing every skill that we've learned up to this point. So in some regards, this would be almost like a semester exam chapter for us. And also ends in some really cool problems called related rate problems, which I'll be trying to sell those to you for a while. And they really are rewarding when we get these, and they're some really neat real-world application problems. So you'll see what calculus can really do for us. So anyway, just as always, math theorems oftentimes are more complicated until you see some examples of. But I'm going to talk through some of these, and then we'll take a look at some graphs. Definition of absolute extreme values. Let f be a function with domain D, so we have some predefined domain. Then f of c is called an absolute maximum on D. If and only if f of c, now understand f of c is a height. So what this says is that the height at c is bigger than or equal to all other choices for heights. Well, that makes sense, then that should be an absolute maximum. Absolute minimum value on D, if and only if the height at C is smaller than or lower than all of the other possible heights when we select any value of x. So all they're saying is probably exactly what we would have thought before we read that, is that f of c is a maximum, that's a y, that's the highest the graph gets if it's higher than every other point. So pretty simple. So if we take a look at this, and we'll come back and forth between this, if I'm looking at, say, this blue graph here, and it's defined on my interval, if we say this is negative 10 to 10, the absolute maximum clearly is 9 over here. This is a little 10 by 10 grid, so we're just going to say our unit measures or our tick marks are 1 apart. So it's 9. We would say that it has a maximum of 9 at 10. We might list the ordered pair, but we should state the maximum that they're asking for is 9. And its minimum is, of course, over here at negative 5. So oftentimes on intervals makes sense that our maximum or our minimum could just be at endpoints. If that's the case, to be honest, we really don't need calculus for that. But let's take a look at, for instance, the red graph. On the red graph, our absolute minimum is negative 7. It occurs at 10. So our absolute value is negative 7 out here at an endpoint, but our absolute maximum of this red graph occurs out here somewhere. Somewhere here is our peak. It might be at 1, 2, 3, 4, and it might be something like 4.15 or something like that. So let's come back and talk about that point in just a bit here. So our absolute maximum occurs at this little black dot. Let's look at our orange curve. Our orange curve, the endpoints are neither the absolute maximum nor the absolute minimum. Our absolute maximum occurs right here, and our absolute minimum appears like maybe it's at 2, negative 7. It's somewhere right around in there. Occurs right here. Okay, on our green graph, if I track it to this corner point, which might be a cusp, it might be implying that we're approaching infinity here, but cusp, corner point, either way, we've discussed those. We'll come back to that. Absolute minimum occurs over here, but the absolute maximum is at that cusp point, assuming that that was not an open circle. So at that cusp point, and at this point, and at this point, here we have what are referred to not only just absolute maximums, minimums, but they're also called relative max and minimums. But one thing we know, let's hold off on this cusp point for a minute. At these other ones that are just continuous and not corners, one thing they all have in common is the slope at that instant is 0. Now, one thing to keep in mind, we could have another curve where the slope approaches 0. Let's say it's just defined here. And I come up, and let's say it completely levels off and then heads back up. So we have a total leveling off point here where the slope is 0, but that is neither an absolute maximum nor an absolute minimum. But we're going to be interested when slope is, if we're looking for these maximums and minimums, for as far as the absolute extreme values, we'll talk about relatives here in a moment, relative minimum maximum. We're going to be looking at endpoints, and we're going to be looking at where we have slopes of 0, or this has an undefined slope here, because we could put a tangent line. I mean, how do we know how to put in our tangent line? There's lots of lines that could appear to be tangent to that. That would be a point of non-differentiability. So if we find a derivative, and let's say it includes a denominator in a term of, say, x plus 4, that would be something that might be happening here. We can't differentiate at -4. That might be an indication that we have a maximum or minimum at that point. So, and then we're going to just test heights at chosen values of x in the initial function. Okay, so we may come back to that. All right, so the extreme value theorem. This one really, I mean, it sounds like, and it is a very, very important calculus theorem, but it sounds like it's going to be earth-shattering, and this is going to be something we're going to go to, and not that we're not going to, but let's take a look at it. If f is continuous on a closed interval, so we can draw it without lifting our pen, and closed interval becomes a player there, closed interval, AB, then f has both a maximum value and a minimum value on the interval. The only thing that might be confusing about that is that the maximum value could repeat. Just consider the line y equals 7. Y equals 7 has a maximum value of 7. It also has a minimum value of 7. So it doesn't necessarily imply that there is a single unique maximum location of a maximum. There's clearly a single maximum, clearly a single minimum, but it may occur multiple times. Imagine the graph of y equals sine of x from, say, 0 to 60 pi. It's going to reach a maximum of 1 multiple times. Okay, and then when they talk about local extreme values, local extremes, relative extremes, you'll hear that discussed that way. That's kind of my habit, is calling it relative extremes. I'll try to convert to our book's terminology of local extremes. And we've spoken about those. We talked about just parabolas. Parabolas that are functions always have a local extreme at the vertex. It's either a local minimum or a local maximum. And what I often say, it just means that you either live in the most valuable house on your neighborhood or the least valuable house on your neighborhood. So this point on the green graph, this one is a local maximum. Now, as it turns out, it's also the absolute maximum. Let's see, this blue point, provided that it's not an open circle, provided we exist at 10, that would be a local maximum, but it's also an absolute maximum. But this point, never mind, this point is a local maximum of the orange graph, but it's also a maximum. Let's take a look. Here we have another one I didn't mention. Here's a local minimum right here. Tangent would be horizontal to the x-axis. This is a local minimum, but it's not the minimum of the graph on the defined domain, -10 to 10. The absolute minimum is over here, the local minimum here. Okay, but once again, if we're finding these, what are the things we're going to need to look at? We're going to need to look at our starting point. Might be a local extreme. We're going to need to look at any point where the slope is 0. It's not a starting point. That might be, it might not be, but it certainly is an indication that it could be a local extreme or perhaps a maximum extreme, as this is. And we have to look at points of non-differentiability where we have a corner point, because if we have a corner, we might have a max, we might have a min. So those are the things we're going to be looking at and doing some analyzing of. Okay, so that is our local extreme values. And then take a look here. This one should make sense now that we've seen the graph. If a function f has a local maximum value or a local minimum value at an interior point C of its domain, and if f prime exists, if it's differentiable there, then f prime of C, the slope is 0. Now that doesn't mean there's only a maximum or minimum when the slope is 0. Remember, if the slope is undefined. So let's look at critical point. This is a term we're going to use quite a bit. Hey, find the critical points. A point in the interior of the domain, so not at the endpoints of a function f, at which the derivative is equal to 0 or the derivative does not exist is a critical point. Great name for them because those are going to be critical for what we're doing in Chapter 5. And definition of a stationary point, probably exactly what you would think. A point in the interior of the domain of f function where f prime is 0 is called stationary. So stationary, 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 stationary. Where the derivative is 0, stationary. So this is stationary, and oftentimes stationaries are maximums or minimums, but they don't have to. So stationary points occur when the derivative is 0. Okay, use analytic methods to find the extreme values of the function. So we know we're going to need to find our derivative. I'm going to start with that. So let's find f prime of x. F prime of x, if I think of this as x to the negative first, this is negative 1 times x to the negative second, negative 1 on x squared, plus 1 on x. So we are on an interval from 0.5 up to 4. Things we're going to have to check. We're going to have to find out what our endpoint values are. So I'm going to need f of 0.5, which is 1 on 0.5 plus ln 0.5. I'm going to need to find f of 4, which is 1 on 4 plus ln 4. And I'm going to need to find any place the slope is 0. So if I set this equal to 0 in any place that it's non-differentiable. Now, this would be non-differentiable clearly if x is 0. But x cannot be 0, so I don't have to test f of 0. You might have, if you weren't looking at this, you'd say, well, since it's non-differentiable, since 0 is undefined here, then maybe we have to look at f of 0, but since the derivative doesn't exist, in fact, the function doesn't exist at 0, we don't have to find that one. But let's set this guy equal to 0. Find our stationary points. And I might be tempted to multiply both sides by x squared, and I get negative 1 plus x equals x squared, or equals 0, excuse me. 0 times x squared is 0. And if I add 1 both sides, I get x equals 1. And I say, well, put in 1. Holy cow, if I put in 1, I get negative 1 on 1, negative 1 plus 1 on 1. Oh, yeah, that is 0. Does negative 1 work? Wouldn't matter, but negative 1 doesn't work for us. We get negative 1 minus 1. So we need to check f of 1. So f of 1 would be 1 on 1 plus ln 1. So we go to calculator on these, don't have to on this one because this is 1 plus the exponent that turns e into 1 is 0. This is just 1. And now we could try to do some analyzing, and we could say this is 1 on 0.5, that's about 2, and I add, well, e to what power is 0.5? That's going to be some negative number, but let's just go ahead and cheat on this one. Let's second quit out of this graph, clear this, get a nice clean slate. And I'm going to go 1 divided by 0.5 plus ln 0.5 is, and for, of course, AP calculus, otherwise requested, we're going to round to 3 decimal places. 1.307 approximately. Let's go 1 divided by 4 plus ln 4, and I get 1.636, and therefore we discover those are the only 3 possibilities where we have maximums or minimums. It's also the only 3 points where the graph levels off. So there's no way this graph, as we move from, let's consider this for a second. 0.5 is my smallest. I move to 1. And I move to 4. At 1, I'm up 1. At 0.5, I'm up a little bit further than that. And at 4, I'm up even further than that. So the question is, does that mean that at 1, this is a relative minimum? I know the slope's 0 here. Might it go down further and come back up? It can't, because in order for that to happen, in order for it to go down further and come back up after it stays stationary, is for it to level off again. And if it levels off, it has a slope of 0. So we have a maximum at 4 of 1.307, and we have that is our extreme maximum. That's actually our maximum. We have a minimum at 1 of 1, and that is also a relative minimum relative to those around us. Actually, we could call 4, because the graph goes to 4, we could call 4 a relative maximum as well. And we have 0.5, which is kind of an interesting point, but it most certainly is not a maximum or a minimum. So both of these would be our, let's go back to our front page here, both of these would be our absolute extremes. So these are absolute maximum, absolute minimum, but they're also relative to those around us. Anything that's an absolute maximum is going to be a relative. So we would just call those maximum, minimum. Okay, so hope that gives you a good feel for where we're going with this. Let's go ahead. We know if I put in 0 here, yep, it exists. ln of 1 exists. Up to 3, this graph exists. It's continuous through there. I'm not going to have to worry too much about places where it's not differentiable. From 0 to 3, I'd have to worry if we'd go back to -1. So let's go ahead and find our derivative. H prime of x wants to be 1 on x plus 1, then times the derivative of x plus 1, but that's just 1. So we need to find the places where that is 0, but we also know we're going to have to find h of 0, h of 3, and h of 0 is ln 0 plus 1. ln of 1 is the exponent that turns e into 1. That is 0. And then h of 3, that would be ln of 3 plus 1. So did we just have ln of 4? No, we didn't have ln of 4. We had ln of 4 plus 1/4. I could probably do some subtraction there, but I'm just going to be lazy here. ln of 4. And we get 1.386. And now we have to find where this function is 0. Well, 1 on x plus 1 equals 0 when 1 equals 0 if I cross multiply. It doesn't happen. Remember what logarithmic graphs look like. This thing is going to look something like, at -1 I've got an asymptote, this thing's going to look something like this. It's never going to level off. So in that case we have because we only get to start at 0, we have a absolute minimum at 0 of 0, and we have an absolute maximum at 3 of 1.386. Again, it wouldn't be wrong to call those relative minimum, relative maximums. That has a lot to do with the fact that these are equal to's here. If those aren't equal to, we can't call them maximums or minimums on that interval because they don't ever get to 0 or 3. Okay, at any point, it's a good place probably for you to pause if you're feeling comfortable with this, but I am going to continue on. So I'm going to find f prime of x, that is 2/5 x to the -3/5, or 2 on 5x to the 3/5. And we're dealing from -3 to 1. And at some point you may want to look at calculators, like what exists, what doesn't exist. Can I put in negative values down here? Well, a negative to the 3rd is a negative, and the 5th root of a negative, it doesn't mind having negatives in there. Can I put in 0 down here? Well, the 0 doesn't mind the being raised to the 3/5 or times the 5 0, but it doesn't want to be a divider. So we do have issues at 0. A fraction is only equal to 0, so the graph only levels off when we have a fraction when the numerator is 0, provided the denominator is not 0 there, and that's never going to happen. Therefore, once again, we don't have a leveling off point here. We don't have a point of we're not going to have a stationary point where f prime of a, for instance, or f prime of some value is 0. Okay, so we need to find f of -3, f of 1, because again, if we set this equal to 0, we get no solutions, but we also have to find x cannot be 0. It's not differentiable at 0, so something interesting is going on there. So we also need to find f at 0. That might be a corner point or a cusp. So f of -3 is -3 to the 2/5. F of 1 is 1 to the 2/5, which is, of course is 1. And f of 0 is 0 to the 2/5, which of course is 0. So let's just find our approximation for -3 to the 2/5. And I go negative, whoops, I better put that in parentheses. Clear, clear, clear. Parentheses, -3 raised to the 2/5. And I get 1.552 approximately. Okay. So there are possibilities for maxes and mins. Well, 1.552 is a maximum, 0 is a minimum, 0 is contained inside the domain, 1's an endpoint, but it's neither a maximum nor a minimum. So we have an absolute maximum at -3 of 1.552, and we have inside here, this is a relative minimum, but it's also a minimum. Okay. Now, if this 0 was somewhere between 1 and 1.552, it's neither it's neither an absolute maximum or minimum, but it could be a relative max or min. But in this case, it's an absolute and a relative min. We have a minimum at 0 of 0. Let's take a look at the graph of this. We could do this by hand, but in the interest of time, let's just clear this out, and I just get x raised to the 2/5. I'm just going to do this in Zoom Standard and see what we got here. There's kind of that indication of what might be a cusp out where the slope is approaching negative infinity. Maybe I'm going to zoom box this guy a little bit here. If I zoom box, I'm going to come over for a ways. Maybe about right here. Just trying to get a little bit better look at what's happening at 0, how steep that curve appears to be getting. I didn't want to do that. Rats. Let's see. Let's do that again. Zoom box. Might as well start there. And you start to get a feel, and we know it does actually get to 0. 0, 0 is on the curve. We start to get a feel. Yes, maybe that is a true cusp point where the slope is infinity. Okay, and more of the same. This is right in our wheelhouse here. We've got a parabola. Find the extreme values of the function and where they occur. Notice no domain. What do we know about this thing? I could go to sprinters, intermediate runners, distance runners, and get a graph of this guy. We could get this from our calculator, but I know this wants to start up at 9. I know it's going down pretty steep, but I also know it wants to turn around and come back. So it starts up 9. It wants to look like a line with slope -8, but then it wants to look like twice as tall parabola. So there's a battle going on here where it's trying, there's no battle going on to the left. To the left, it just wants to go up. To the right, this is bringing it down, but passing the baton to this that wants to take it back up. And I don't know if it gets down to 0, but I know that it has a shape something like this. Again, maybe it gets down, but we're really not interested. I mean, we'll find that when we find this value. But this thing does not have a maximum. In both directions, it's going to be approaching infinity, but infinity is a concept. It's not a number. We can't say that the maximum is infinity. It is approaching infinity. So it has no absolute maximum, but it does have an absolute minimum and a relative minimum, and that occurs at the vertex. So we could do this without calculus. We could opposite of b over 2a, but we could also go ahead and say, well, let's find y prime. Y prime, the slope of this becomes 4x minus 8. We set that equal to 0, and we get x equals 2. This occurs at 2. Now, maybe it's not up here. Maybe it's down. So the only point that we know of, we've got an absolute minimum, a relative minimum. We've got a minimum at 2 of, well, we need f of 2, or we need y equals 2 times 2 squared minus 8 times 2 plus 9, or we get 8 here minus 16 plus 9. When you're finding these, I think I've spoken about this a number of times, but if you're working with parabolas and you put the x value of the vertex back, these should always be opposites, and this will always be double that. So I get negative 8 plus 9, and actually my graph was pretty decent, of 1. So we have a minimum. It is a relative minimum. It is an absolute minimum. And while you get a lot of practice on these, at some point I think you're going to get the gist of this, but certainly worth going through. If you do feel like you have it, it'd be a really good time to just go ahead and try one on your own. We're, again, finding extreme values of the function where they occur. This function exists forever. So I'm going to go back to my little sprinter, intermediate runner, distance runner hieroglyphics. I know I start up at 5. I know this wants to go down steep again. I know it wants to continue down in both or try to go down in both directions. I don't know if that x squared will overcome this minus 8x that's trying to take it up to the left. But I know eventually it wants to look like a positive cubic. So there's going to be some questions here. We may need to look at the graph, but I'm going to try to avoid looking at the finalized graph, like the actual thing. I'm just going to give myself kind of a shape of what's going on here. So let's take a look. We start up 5. We're going down really steep, trying to turn back up. I just had one similar, and it got all the way down to 1. I actually think this is going to get, so right now what am I doing here? This x squared wants to go up in both directions. So I know it wants to go up down to the left, eventually giving way to up to the right and more up to the right. This is pulling up harder. I don't know if it's going to get down to 0 or not. I really don't know. But something like this. I'm certain we're going to have a relative minimum over here. Now, as I move to the left, it wants to go up more, and eventually, though, we're going to give way to this x cubed. Eventually, it's going to come back down. So I really suspect we have, well, I'm certain we have no maximum, no minimum, but I'm also certain that we should have a relative minimum and a relative maximum. Y prime, 3x squared plus 2x minus 8. Pretty cool, because if you took honors pre-calculus last year, whether you took that with me or whether you took that with Mr. Hartz, you were doing this problem in chapter 2. We didn't know what derivatives were. We just called them the special slope formula thing. Factors of negative 20, this might actually factor. Factors of negative 24 that add up to be positive 2 are positive 6 and negative 4. And I can get a positive 6 if I steal a 3 from here and a plus 2 from that 8. There's a 6. First times first equals first x. Last times last equals last minus 4. There's my missing negative 4. You can check it. We want that to be 0, and that gives me x equals 4/3, or x equals negative 2. So this point is 4/3 something. I don't know what. I don't even know if it's negative. And this point is negative 2 something. And what is left for us to do is find y of 2. So at 2 we've got 2 cubed plus 2 squared minus 8 times 2 plus 5. At 4/3 we've got 4/3 cubed plus 4/3 squared minus 8 times 4/3 plus 5. I'm going to be a little lazy on this one, but this top one, 8 plus 4, 12, 12 minus 16, or I could go 12, 8 plus 4, 12, plus 5, 17, minus 16, 1. And that is, oh rats, you guys caught that. I know you did. You guys caught that. That's negative 2, negative 2, negative 2. So it's not going to be that. Let's see, I get negative 8. I'm just going to jot it down here. Negative 8 plus 4 plus 16 plus 5, or 21, 25 minus 8, 17. Seems like it should have been higher than 1. Well, of course, because it was at 5 here. Okay, and then I'll just be lazy on this one. I know all of you would like to work out with the fractions, so you can go ahead and do that on your own. Second, quit, clear this, and we're just going to go 4/3 to the 3rd, and we'll change this back into a fraction when we're done. Step out of that, plus 4/3. Yeah, yuck, yuck, yuck. Let's delete out of that. Insert 4/3 squared minus 8 times 4/3 plus 5, and we get that as a decimal. I'm going to go ahead and write it as a fraction, math fraction, about my favorite, negative 41 on 27. So yep, we made it down below 1, not quite, about down to a negative 1.5 here. We're up 17, those are believable. So we have a relative maximum. It's definitely not the maximum. That is not going to beat this guy. We have a relative maximum at negative 2 of 17. And we have a relative minimum. It's not going to be more minimum than that, at 4/3 of negative 41 on 27. Apologies there. We might need to zoom out here just a little bit. Bear with me. So hopefully that's a problem, makes a lot of sense to us, because it's something that we'd be at least somewhat comfortable with. Okay, this one, maybe we don't have that much experience with square graphs with squared terms in them. So I'm going to be thinking of this as x squared minus 1 to the 1/2. Again, we've got some issues here because they aren't telling me domains. We don't have necessarily endpoints. So I'm going to do some little analyzing before I go any further here, because x squared minus 1 has some issues. I know that x squared minus 1 has to be greater than or equal to 0. Therefore, if I treat this as an equality for a moment, x squared minus 1 equals 0, I get x squared equals plus or minus 1 on a number line. Here's negative 1, here's 1. If I put 0 in here for x, I've got problems. If I put 2 in here for x, no problem. If I put negative 2 in here for x, no problem. Our graph is okay out here and here. So it's implied, they don't have to state the domain restrictions, but it is implied that x is less than negative 1, or x has to be bigger than, it could be equal to, bigger than or equal to 1. Okay, worth noting, because there may be some places that we don't have to test, but that makes those endpoints for us. Those are endpoints of the curve. The curve stops and starts again at negative 1 and 1. So it's something that it's not just something that we might want to consider, it's something we have to consider. Okay, let's go y prime. Y prime is 1/2 times quantity x squared minus 1 to the negative 1/2 times the inside derivative 2x, or 1/2 times 2x, x, on square root of x squared minus 1. And what's that tell us? We have the same restrictions here, but at 1 and negative 1, those are okay, they survive the square root, but they make this 0. It's non-differentiable. So we would test those points because it's non-differentiable at 1 and negative 1, but we're going to test them because they're endpoints of this curve anyway. So I'm going to call it f of, if I call this f of x equals. So we're going to find f of negative 1. We're going to find f of 1. And now we have to consider when this is 0. Well, this is only 0 when the numerator is 0, but the numerator can't be 0 because we got problems in the denominator. Plus, we knew ahead of time we can't be in this zone. So the only 0 for our derivative, the only place where the slope could be 0, isn't defined on our curve. So we're only looking at endpoints. The graph does not level off anywhere out there. So it takes only a moment to know when we put 1 in here, when we put negative 1 in here, we get square root of, for instance, negative 1 squared minus 1, we get 0. We get square root of 1 squared minus 1, we get 0. So our graph has points here, and those are either going to be maximums or minimums because nowhere else does it level off. Well, what happens is I put a bigger value in here for x. If I put a bigger value than 1 or a smaller value than negative 1 to the left, this becomes bigger than 0 inside of here, and our graphs are going to go up. How do they go up? I don't know, but I know they're going up. We might know, but I know they're going up. I don't think they're going up linearly, but they're going to get bigger. If I put a billion in there, it's going to get bigger. A trillion, it's going to keep getting bigger. So there are no relative maximums, but there are relative maximums or even absolute maximums, but we do have these absolute minimums. We have minimums at plus or minus 1 of 0. And maybe worth plotting some points or going to your graph and taking a look at that. We should be able to confirm everything, and we're going to have some more challenges as we move on. We should be able to confirm everything, even whether it's a minimum or maximum going up or down, without looking at our calculator, but that could be a real point of comfort for you to take a look at that. I'm going to stop this video and proceed with this on part 2.